Are you off mute?
Yeah, we're off mute. Actually, a little early for once. So, there we go.
Yay!
So, we are back looking at the programming we did on our little rocket. In Simple Rockets 2, this time we're looking at this programming language called Vizzy that's included with Simple Rockets 2. Last time we put together our whole flight plan, right?
Yeah.
And then test flew it off of the planet Drew, the default planet, somewhat smaller than Earth.
Right.
So tonight we will launch from Earth, since we have installed the real solar system update, or mod, or I'm not sure if it's a mod exactly. Anyway, you get to choose what solar system, and now I'm picked Earth. So we're going to see what our rocket would do on Earth.
On Earth.
Well, taking off from a more accurately simulated Earth.
Okay.
But we'll get to that. First, we'll do a little comparison of the code here. What I wanted to talk about is we generally have the idea down that this simple program goes from start and then calls each one of these functions. They call them custom instructions. In C, and embedded C, it's a alternately referred to as a function, a method, and a procedure, depending on who you talk to and how accurate they want to be about it. Function comes from mathematics, which is to say that you have some formula that you want to calculate, and it's a function. The big script F that you see in mathematics a lot is a symbol for function. And it usually is a function that goes from 0 to infinity, or it's a calculus thing. So, of course, when I was first getting into computing, they were...
How big are your toes?
I don't know. I'm big enough.
Hi, Flask.
So when I was first getting into computing, the whole point of the computing was to do these heavy calculations for you, and sort of prove out the calculus, if you will, or let the calculus do the calculus quickly. So a lot of what was the terminology of computer programming came from mathematics. So a function is some amount of mathematics done and a value returned. A procedure is just a series of instructions done in a sequence.
Right.
A method is kind of similar to a procedure. It really is just a sort of different terminology that came with object-oriented programming. In a lot of cases, a method would also not be able to return a value specifically. But procedures and functions, custom instruction, they're all roughly the same thing in these various programming models.
Interesting. So, do you do software development professionally? Flask asked.
Yes, I have been in software for 35-ish years. And the last 25 of it being in embedded software engineering for
aerospace
software, mostly in the graphical world, but also down at the operating system level. So I was just having fun with Simple Rockets 2. I thought it'd be a good little instructional platform. So getting into this one custom instruction we created for the countdown, right? It's pretty straightforward. In fact, we could actually simplify this.
He says it sounds incredibly interesting.
Oh, cool.
It is.
Well, glad you like it. We'll we're just sort of getting into this and seeing how we feel about doing it this way.
How I see. That's exactly how I see programming.
Is
Yeah, is this.
so this makes programming understandable. Is what you're
Yes,
saying?
to my brain.
Yeah, and that's probably why a lot of people, and myself included, had envisioned a system like this. And I think Vizzy is specific to simple rockets, but there are other variations like of this programming style, visual programming style. I think there's no reason that I couldn't take the XML file that this produces and turn it into C code, and then use it on the actual hardware. no, no limit other than time and coding. It would be an interesting project, though, if someone would take this, because this is saved in an XML file, which is a text file, which is readily parsable by various software on the web. So it shouldn't be too difficult to build a translator. Although there are some key differences that we'll get into in a second. So first off, let's bring up our code window. So unlike this nice visual programming,
Yeah.
what we program in is text. Ooh, what fun. So by and large, the concepts are all the same. They're just syntactically different in the text world. It's syntax. In the visual world, it's shape and how they interconnect, I guess.
Well, those things all mean stuff, though.
Right. So I actually noticed that one thing I have here is a comment.
Void countdown.
Right? So this has a method of a comment section as well.
Right.
I don't know that it's multi-line.
Countdown procedure, 5-second countdown with throttle.
So I'm going to block and copy this. And this is all hotkey driven, right? Poof.
You can write C in simple rockets?
No, not yet. But I think it'd be pretty cool if you could. It ain't nothing but a data processing program.
Still in beta, isn't it?
Well, I'm not sure what. I think this is Simple Rockets 2 pre-release, I believe. It's the Steam version. So it doesn't look like you can make these multi-line. It's a one-line comment, and they use the hashtag that you see up here. And in certain languages, yeah, it's hashtag, but a single line comment in the C language is this double forward slash. And a multi-line comment is anything between these two characters and these two characters. Anything in that sequence would be considered a comment. And I messed it up because here's the end sequence. So if I get rid of that, there you go. See how that custom highlighting happens nowadays? It was not how it started. It was all black and white. The C code that I'm reviewing is stuff that I wrote a couple of days ago, specifically for the stream. It does not compile. It's really just examples of the syntactical differences and the difference between writing.
I see it exactly.
And typing.
I understand exactly
now
what
you
you're
see
doing.
exactly what it does, right? Except you run into some certain little idiosyncrasies that exist in C for various good reasons. Don't exist in Vizzy for various good reasons. For the same various good reasons. So they both have their place, right?
Yeah.
So in this case, we have that comment character, which we showed up here. A custom instruction in Vizzy is a void countdown. Now, the reason the keyword void is here is because every function or sub-procedure or subroutine is the other term for a procedure, by the way. Procedure, method, subroutine, function. In the C language, they all can return some value, right? A single value of some sort. So it could return nothing. And in this case, this is how you say that it returns nothing. It returns a void. Weirdly, there's also another term for nothing in the C language that's called null, which actually is also numerically a 0. I don't know why void. Go figure. That's Carnegie and Ritchie came up with that term. So those are the guys that created the C language, like back in the 70s. So in this case, the countdown doesn't return. None of the custom instructions actually return a value in Vizzy, at least not that I've been able to find. It might be helpful, might not. They have a different concept called a custom expression, which does return a value. So we're taking way longer than I thought. But here we go. Anyway, countdown. Now we can't have spaces in the titles in the function names. I'm just going to refer to them as functions from here on out. You can't have spaces in the function names in the C language, but you can in Vizzy. So I just substitute underscore for space when you have to. And then because the countdown doesn't have any parameters, which slow pitch over does, it has a couple of parameters. But since countdown doesn't have any parameters, it's just empty. Now, if you want to be exactitude about it, that's like the exact way you're supposed to do it. But that gets over. That just takes up extra characters, right? So in this function, everything within this curly brace and this curly brace.
Is it called a curly brace?
Yes, those are curly braces.
All right.
Everything between these curly braces is the body of the function. So this would be the return value or the return type. We'll get into types in a minute. But then the function name, the parameter list, then this is the body of the function, which does various other things.
All those functions.
Calls other functions, etc. Right.
Right.
So in here, there's not really a body indicator for the custom instruction, like there is a body indicator for the repeat. What would they call these things? Divisions. In HTML, you'd call them a division. I forget what they actually refer to each group of pair of curly braces as. But in this case, it's the function body, whereas lower down, it's the body of a while loop or a while function. So clearly, it's pretty straightforward, right? We just display 3, we printf 3. Printf is a special keyword in the C language that allows you to print a formatted string, hence the F. In this case, we're not doing any formatting, so it's just a straight string of characters. This is drawing a blank on the name already. Notepad++. Keep wanting to say simple something, but it's not. It's Notepad++.
What is the editor you're using there for the C code?
Notepad++, it's freeware.
Freeware.
Provides all this nice syntax coloring and the ability to compress the bodies of functions and things like this. Of course, back in the day, you just typed it, right? So we printf 3. So printf is an internal function, a common function within the C language.
Yeah.
That's for doing output like this. But then this wait 3 function, that doesn't actually exist in the C language. So we had to create it. And what something like this is, in this case, they have a custom instruction, wait 3 seconds. What that amounts to is a function that's specific to the hardware, right? Because it's 3 seconds, and how do you know what a second is? Right? Or how do you know, I should say, how do you know when a second has elapsed? So typically, your code like this would have some system interface code, and sometimes called a hardware abstraction layer or an OS abstraction layer. And it provides the OS-specific version of a wait function. So here's our wait function. We want to wait a specified number of seconds, right? So it's kind of like a custom instruction. It doesn't return anything. The keyword is wait, or the function name is wait, and we want to put in some number of seconds, right? So this int right here is short for integer, and what that is the data type. In other words, it's an integer number 0 through some large number. Typically, well, in this case, it's an integer. On this hardware, an integer is 32 bits. 30, and this depends on your compiler and depends on your hardware, whether it's 32-bit or 64-bit. It's just like the Nintendo 64, right? Was 64-bit, and so almost everybody on desktops are 64-bit now. A lot of the embedded targets are still 32. So typically that's 32 bits. That means that you can specify a number, and since it didn't say unsigned, this is a signed integer, which means it goes from the possible values are negative roughly 2 billion to positive roughly 2 billion, because the entire numbers, if it were unsigned, could be from 0 to roughly 4 billion. So anytime you have a signed integer versus an unsigned integer, the unsigned is twice the numbers, and the signed is just half. And we don't have to get into the reasons why. That is, you just have to know really at this point that integer is a number versus a string of characters meant to be something you would read. So, yeah, plenty of range for the bank account balance, that's for sure. So we're going to pass in a number, meaning seconds, right? And so the first thing we're going to do is say, I want to create another number called in time, and I'm going to get the current time in milliseconds from some piece of hardware somewhere, right?
Right.
Which, you know, in this case, we'll say, what was that? Well, get time in milliseconds. We don't know what the body of this function is. We just know that this is how we would call it. And this is what they refer to as a function prototype. It's exactly like the first line of the function body, except with a semicolon at the end, and no body specified. And what this tells you is, if you wanted to get the time in milliseconds, it's this particular spelling. This is the word, the function to do that with. But you don't need to know the underlying bits and bytes of this, how it goes about flipping bits to find the actual number, right? You just have to know certain things, like it's in milliseconds, which means 1,000. You have to divide by 1,000 to get seconds. And it's, in this case, the number of milliseconds since the system power up from some hardware timer. And now, whether it's a hardware timer or a software timer, that's actually dependent on your hardware and operating system. But in any case, that's how we get the number of milliseconds since we launched. Oddly enough, for the longest time, date on the PC, the date function, was the number of seconds since midnight 1970.
Right.
And that apparently runs out in like 2044 or 2035 or something like this, because it becomes 4 billion, which is the number of seconds that you can hold in 32 bits. So, in any case, that's the 2035 problem instead of the 1999 problem, Y2K problem. It's the Y2035 problem. Which apparently is coming up. I didn't realize. I hope that worked. Okay then.
Yeah.
So we get this wait time, right? We're back in wait time. We decide to create a new number variable that's of type number, and we say get the current time in milliseconds, and then add to it however many seconds that was passed in times 1,000, because the ticks are 1,000 ticks per second. So what this does is it basically says calculate what I should be waiting for, right? What's the end time? You passed in this case, we passed in 3, right? We pass in 3, so seconds is 3. Seconds times 1,000 is 3,000. If we got the time in milliseconds and it was 1,000, then end time would be 4,000. Right? That makes sense?
No, yeah?
No, yeah? Kinda, sorta? Were you following along?
Yes.
Okay. So,
Yeah, I mean,
you get the general idea, right? Basically, it's just like saying, what time is it 30 minutes from now? Just in seconds and milliseconds instead of minutes. So, then we're going to enter into what's called a while loop, right? And while is one of the key words in the C language. And there's a similar version of it here, a while version, which just loops until its condition is no longer true.
Right.
So while something is true, and in computing, true and false, which in this visual language are literally true and
0
false.
and 1.
There's 0. Well, there's 0 for false, and anything else is true. Anything other than 0 is true in the C language, anyway. There's actually a little true and false keyword here somewhere. I forget where. Anyway. Is it in this? Oh, there they are. There's true and false way down there. So, yeah. And it's the reason it is that way is because it basically does a subtraction. It says when you say if you're trying to evaluate whether or not something is true, which we'll do here in a second, actually. But
are you?
Yeah. So what this while statement does is continue while this is true, right? And what are we doing here? We're saying if we get the time in milliseconds, which is now 1,003, maybe.
Right.
Because when we came in, it was 1,000. Well, that's still less than 4,000, right? So this expression is true. Get time in milliseconds is less than or equal to the end time. Now, you notice that this is just typed out, right? Less than, equal to. So if I screw this up, do some testing, and have to come back and make this greater than or equal to, it's just a quick little character flip. And you saw what kind of a bit of a pain in the rear it was to flip out those two conditions here in Vizzy. It took a little bit more dragging and dropping. So in any case. Again, it's one of these things where the creation might take just as long, but the editing is a lot easier and a lot faster. And quite frankly, Vizzy's pretty fast in editing. If I wanted to duplicate or pull an instruction, I can grab any one of these instructions from any other existing instruction, which in this world is called block and copy.
Right.
So you go, yeah, that's how I grab the while. Now you got to make sure you've highlighted everything, right? You don't want to block and copy that, and then you have to go fix it. So you got to make sure you got everything highlighted, whereas here you just right-click and it takes the entire instruction without you. Like if I want to take this repeat, right? I right-clicked, so I created a new one. But if I want to just take this whole section, right, the sections stay together better in Vizzy. It's a little harder to screw them up. Screw up your block and copy, if you will. On the other hand, it is only everything below.
You can't see what you're doing because the page is up in front of you.
Oh. Well, I'm actually over in this. On the page. Oh. That's okay.
Okay for you.
I think all that needed to be in there was there.
Okay.
So
let's shoot it off into
is
space.
what I'm saying. Well, we're getting there.
25 minutes.
Well, I didn't
I ain't
say
seen no rocket yet.
You saw the rocket last time. All right, let's get faster through this. The long story short, we had to create our own wait function, right? There's a couple of other things that are specific to Simple Rockets 2, certain events and things that would also have to be custom implemented, but we won't have time for all that, of course. One of those others is the wait until function.
Wait until.
Yeah, wait until an expression is true, rather than while an expression is true. So it's a slight difference, but not by much, or not too terribly different, rather. So, getting back over to here, there's our wait, our print, our wait. Then we do set throttle to 1. Well, what in the hell is set throttle 1, right? That's not part of the C language, that's part of this system. So that'd be another system interface function. And I just did a generic kind of version of what this might look like. You say set, you say which parameter, roll, pitch, yaw. That's done over here by dropping down the list, right? Over here, you just click on the list, right?
Huh?
And in the C language, you happen to have to remember what these things are and exactly how they're spelled. And in the C language, everything's case sensitive. So exactly how the case is it. I'm going to say case like 1,000 freaking times here. Okay. There's a way of predefining things in the C language so that you don't have to use magic numbers everywhere. So because it's easier to compare numbers than it is strings of characters, things that are constant, like this list of parameter values that can be used. And of course, values that are not these can't be used. Right? I can't pick something that's not in this list over in the Simple Rockets. Whereas I can mistype and misspell throttle as I'm off to do. Right?
Yeah.
So you can see where there's certain advantages in being able to program more quickly because you don't make these kinds of textual mistakes that you generally don't find out about until you block and copy the same command 17,000 times. And then you went to compile, and then it finally came back and said, oh, you spelled throttle wrong 17,000 times. Luckily, you can do a lot of search and replacing. But you don't have that problem with Vizzy. So, but in any case, so you have some sort of set function. In this case, it just says whichever parameter, roll, pitch, yaw, throttle, and then some value. And you'll note these type specifiers, originally we said integer. So parameter is an integer, it's some number, right? A whole number, I should say. And then this is a floating point number. Yeah. We could misspell yaw and y'all, that's for sure.
Y'all and y'all.
So in this case, float means floating point number, which allows you to have some number that's some low, a floating point number. It means that you can have something smaller than 1.
Right.
And in a lot of cases, like it is with the case of the throttle here, a lot of times people will bound their values for a control between -1 and 1. They do it a lot in OpenGL as well. But as a floating point value, so of course it can be 0.0996 or something like that, right? Now, float is a keyword in the C language that specifically means 32-bit floating point value.
Do you do a lot of OpenGL work?
Way too much.
And y'all is not in his vernacular. It's in mine.
No, mine was the Texas version, y'all all, which is the plural. So in our set function, you would check out the first parameter if it were throttle, right? Now we're doing this comparison with this double equal sign, right? what that is to say, is parameter equal to throttle? Well, parameter is of type integer, which means it's a number.
Right.
So throttle has to be some sort of number, right? But we don't want to put in is if it's equal to 1 or equal to 5.
100.
We call
How would
those
you
magic numbers because nobody knows why it's 5, right? So we want to be able to say if parameter is equal to throttle. So in the C language, they have this thing called pound defines. It's actually done by a process called the preprocessor that comes in and looks for these keyword commands that start with hashtag. In this case, this is not a comment. It is a command to a huge search and replace engine called the preprocessor. And it allows us to say things like define that throttle shall be 1. But now, when you compile this, the preprocessor runs through it, says, oh, define throttle is equal to 1. So now, from here on out, every time I see throttle, I replace it with 1, and then I send that down to the compiler to actually compile. So the preprocessor...
It's very low level.
I know. But what it allows you to do is do things like this, where a number, parameter, is compared to a number. But it's human readable in code. Just like this. This says 1 for the throttle. You just happen to know that 1 is fully positive in the range from -1 to 1. That's the biggest positive number. So that means full throttle, and half throttle is 0.5. And I guess there's no negative throttle, even though it has a range of -1. I don't know. I don't know why that is. But in any case, so the parameter might be equal to throttle. If it is, then we call some other embedded function that is specific to your hardware that says set the throttle position to that value, right? So in most aviation, the autopilot is actually controlling the same thing the pilot would normally control. So if the pilot turns the wheel, then the autopilot turns a motor that turns that wheel. Almost as if it was retrofitted, you know? But they do that so that it's the same interaction. And when the pitch and yaw and the autopilot changes anything, the pilot can see the yoke do the same maneuver that it would normally do. And they actually use that in certain cases to warn you about a stall. They have this motor that just pushes on the stick so that the stick is all flapping in your face or rattling in your hands, and that's a warning that you're about to stall. But they do it with this motor that pushes the stick. And they didn't want to put that motor on the 737 MAX, so they tried to fix it in software. That's a long way around to that story from this throttle position function, but anyway. So same thing, kind of thing with pitch. You'd call some function that calls pitch, and that's going to be down in your hardware somewhere. Same kind of thing with these other functions that I didn't get much further into because really I, set pitch position. That's going to amount to any number of different things for whatever different hardware. And luckily, we don't have to deal with all that in the simulation. I just want to give you a taste of what something simple like this countdown function actually
it's not
blows up as when it comes to getting it all the way down onto the actual hardware to do something. So these, in fact, even these printf functions go nowhere unless you have some place to see them. And in the simulator, of course, it just shows it in this line of text at the top of the screen. In here, this would typically come out of a serial port. Yes, a serial port. 9 pins, RS-232, just like it's 1993.
The same.
Yes. And unfortunately, most PCs don't have US serial ports. So we got all these USB to serial port connector things that I buy a new one of about every 2 years. Anyway, getting off track again, right? So, lock heading on, watching the thing fly. So, there's, again, just to break down that countdown function, we got all the way down into the hardware level. So the next function they have that we have here, this slow pitch over function, just to give you a similar, let's see how that, yeah, okay, you can see it. Make sure you can see both sides of it. Alright. So this says similar mappings, right? You can see the slow pitch over. You have first parameter is a step size, the next parameter is steps. And one of the things that we talked about that was different in Vizzy is they have two types of parameters, numbers and strings of characters. And this was true with early Visual Basic, or rather early Basic. They didn't get into the details of how many different types and sizes of numbers you could have. But the C language gives you access to very, very small integers that are 0 to 255, which is 1 byte.
Right.
8 bits. You can get what they call a short. So there's not byte, it's character. That's 8 bits. That short is 16 bits. Int is 32 bits. Long is also 32 bits. Long is 64 bits. They decided not to create a new word for some reason. I don't know why.
Long
Long is 64 bits. So go figure. So here's our slow pitch over function, similar to this custom instruction, right? And he says here, set variable pitch change.
Longer.
Longer. So we're going to create a variable called pitch change, and we're going to set it to the current nav pitch, right? So we're going to have some function in the system that reads the current nav pitch, right? So all it has to do is return that value. And what I mean by return that value is, I didn't do a version of that, did I? So let's see this nav pitch function, right? Nobody wants to watch you write comments, so we're just going to do
commenting
a really
out code is boring.
We're going to do a really simple float nav, and it's pitch roll or yaw, right? So int parameter if parameter is equal to pitch, return pitch from nav, whatever function that is that gets the pitch from the current nav ball, right? Gets it from the hardware. So this is, once you've figured out how to get it from the hardware, this is how you decide when to take that information and return it from this function called nav. See how that sort of flows backwards? So return keyword in the C language basically exits your function early, which is actually a no-no in coding nowadays. You should only have one return point. But you could have if param equal roll, you'd return roll from nav, right? And they actually frown on having 2 return points because it actually means that everything below here never gets exercised. Which you might think, oh, that's being efficient, which is what they used to think. So rather than having to say if the parameter is pitch and then check again if the parameter is roll, well, the parameter is not going to be roll if it's already pitch, right? So it's not going to change in between those 2 times. If it does, something's really messed up in your hardware. So this was considered more efficient back in the day, but it causes certification problems in real systems. So that's our nav function that we quickly added, right, that returns this value. It reads it from the hardware, returns it to our code, and we use it to temporarily store it in pitch change. So we read the pitch from the hardware, we're going to store it in pitch change. It really shouldn't be the pitch up and down can be less than a degree in accuracy. In other words, it can be plus, or it can be down in the tenths or thousandths of degrees. So it should really be a floating point. Yeah, multiple return points can cause certification programs in aviation software. So typically you would set a variable to the return value. You would also, in this case, this would be, you'd definitely say else if, because that's the other way of skipping that function, or skipping that extra bit of code. So I don't know how many times I've created a value called return value, a variable called return value. Probably made it a whole bunch of times. So what that does is it says create a temporary variable, make it equal to whatever value you need to make it equal to along the way, and then return it only once at the end. And also, by using these else if, then this doesn't get run unless this comparison is already compared to be false. If it's true, we do this line, else, meaning else if it's false, which it isn't false, so it doesn't do anything after that. Now, another little tweak of the C language. If you want to do more than one line inside an if or an else statement, you need curly braces. The curly braces help get. That was my. The curly braces help guarantee that you're only doing that segment of code that you intend to do. Right?
Yeah.
By not having the curly braces, you can get away without the curly braces if it's only the next line. But if you suddenly come along later and you say, oh, well, I also need to do blah, 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 right? And you didn't use the curly braces, well, then blah, blah, blah would be run every time, and it would look weird, and you'd be like, why in the hell is blah, blah, blah running all the damn time? Well, blah, blah, blah is running all the damn time because it's outside of the curly braces. So that's why they encourage the use of curly braces, even though you can get away with it like that. Blah, blah, blah will be run every time
Blah, blah,
anyway. Blah, blah, blah. So they encourage the curly braces. Now, you'll see you'll start a fight in the C community if you want to debate about curly brace at the beginning of the line here, or curly braces each on their own individual line. But, you know, they'll complain about that one carriage return all day long, whether it's that or that. Believe it or not, that's actually the only reason we do this is for the human readability. As far as the C compiler is concerned, all the white space is irrelevant unless it's inside quote marks. And so what the C compiler sees is essentially this. That's essentially what the C compiler sees out of that one line. It basically reads into the semicolons, right? That's hence why there's all these semicolons at the end of the lines. So, back in the day, there was a rule at one company I worked at that said for every semicolon in your code, here, here, you needed to have a one-line comment that explained that line. And temp var to allow for single point of return. Ugh. You can see how tedious that can get.
Right.
But that helps with the certification because they want to know why you're doing each line, not what each line is doing, because if you know how to read the code, then you know what it's doing. We're taking a temporary value and we're setting it to the return of this function, whatever that function does, I don't know. It says it's the pitch from the nav. I guess that's what it claims it is. Hopefully they name their functions usefully like that. They don't do like PFN. That's the pitch from nav function. Why? How do I know that, right? So hopefully they name it things like this. But that depends on your hardware and your operating system. So we've got our temporary variable. Oh, this is the nav function. All right, back off here. For a pitch change, we read the nav. This says repeat steps, right? And what we're going to do is we're going to say while the steps is greater than 0. We don't really have a repeat function in the C world. We just have a while function. But we're going to... oh, and I screwed it up even. But that's good. Always good to have a screw up live, right? So we're going to have repeat steps. And then here we set the variable pitch change to pitch change plus step size. So that's almost identical, right? We set variable, well, that's pitch change equals. And pitch change plus step size is pitch change plus step size. Now, if I could just reach in to Simple Rockets 2 right here, where this plus sign is, and like right click on it or center click on it and change that from a plus to a minus to a times or an equal or what have you, or a divide rather than having to replace the blue segment, that would be helpful. Because it's so easy to change this if I made the mistake. It's easy enough to change back and forth. Again, minor difference. So we're going to go in here while steps is greater than 0. So when we first came in, we said the first time we call this function is in the ascent stage. Over here, we call slow pitch over -115 is the two parameters we pass. Is that visible? Yeah, there's the first time we call slow pitch over. So the step size is -1 and the steps is 15 coming into this. So we're going to set this to the nav pitch, whatever that is. Doesn't really matter. Say it's maybe 0. It's actually 90 when we start off. So because it's pointing straight up. So while steps, which is currently 15, is greater than 0, we're going to take the pitch change and we're going to basically add the step size to it. Now, I didn't notice this until later that Vizzy has a function, both two things, the set variable function, but it also has the where'd it go?
What are you looking for?
There it is. Under variables. You'd think. So this is where in Vizzy I went to define the variable pitch change, and another one that I eventually threw away. So I use this function change variable blank, or rather set variable blank to blank, right? That's what I had originally used. Set variable pitch change to pitch change plus step size. And over here in the C side, I said pitch change equals pitch change plus step size. And the way C evaluates functional expressions, it understands parentheses. And so that's kind of what they're showing here with the little blue box, is that it includes pitch change and step size. And it would be legal in the C language to use a pair of parentheses like this. It's just redundant. It's not needed. It is needed if you then want to multiply it by 5, right? If you're going to multiply that by 5, the parentheses matter versus doing this. And that's because it'll do the multiply first in this case. And in this case, it'll do what's in the parentheses first. So that's all complicated. Not complicated, but that's a little bit more in depth about software engineering and or not. What's the term I'm looking for? Order of operations of mathematical evaluations, evaluating mathematical formulas. So this is a mathematical formula, not a complicated one. But it says take the current value and add some value to it. Now, they had set PIDMath, the parentheses, exponent, multiply, divide, adding, subtracting, the order of operations. So, let's see, where were we? We were adding the step size, and then we would set the craft's pitch to this pitch change, right? That's essentially the same function here. Again, set craft is some craft-specific function. And then we wait this 0.1 second, right? Now, in our version of wait, we had it as an integer, so we actually have to change that. So that wasn't just the thing I got wrong. So this can't be an integer because that's a whole number. We want it to be 0.1, so that needs to be a float. And of course, if that's a float, then our end time needs to be a float. Right? And there's another little formula, right, that we did. So it's these kinds of formulas in mathematics that they wanted to create computers for, so they could put in a version, what's the answer, what's this calculation, what's this calculation if seconds is 1? What is it if seconds is 2? Now let's do this 1,000,000 times, right? That's what computers are good for. So we've this also presumes that get time in milliseconds is a floating point number, but it probably isn't. So, but that's okay because, well, it may not be okay. It should be okay because if I put in 0.1 for the seconds, 0.1 times 1,000 is 100. So yeah, that's still some integer number of milliseconds later. But I'm not going to be able to get down into that fine granularity with this level of function. And that's something that you deal with in real-time systems and real embedded systems, whether or not you can time that quickly. That's why they don't use Windows in real-time systems, because for the longest time, Windows couldn't do anything real-time, meaning it couldn't do anything that was faster than every 10 milliseconds. 10,000ths of a second. And in computing, or in control systems, you regularly do things once every millisecond, once every 1,000th of a second. You want to do something, check on something, get a value from how fast you are going, what have you. And then sometimes, your fuel level, maybe it only responds once every quarter of a second, every 250 milliseconds. So sometimes you want to do things quickly, sometimes you don't have to do them all that quickly, but you want to do them on a consistent basis, immediate, if every 10 milliseconds do the same thing. And the Windows operating system was never designed for that. It was designed for human speed, not computer speed. So even Linux wasn't designed for that, hence why there are various embedded operating systems for safety critical, time critical kind of operations. So enough of that. Anyway. So we get back to this. You see the basic functionality where everything inside this set of curly braces
Yeah.
Inside the while loop is indicated by this blue bar
Yep.
over there. Now, what this function did was said repeat some number of step times. I couldn't do that, but I said repeat it some number of, as long as step is greater than 0. Well, right now, if we come into this code, we never touch steps in any of these lines. So what's steps at the end here? Well, it's the same as what it was to begin with.
Window. What was the embedded OS you use, or?
Oh, that's a long story.
Is that even the right question? Give me my water back.
So, embedded OSs, safety critical embedded OSs, based off of my order of running into them. No speaking as to which one's better than the other. I'm not going to give recommendations here. They each have their own pluses and minuses for different applications. That's the best way I'm going to put it. But in order of appearance, QNX, the operating system of Nokia, which went foof along with Nokia, then Integrity from Green Hills, which I sold for some years. I was the field engineer, which is the technical guy that showed the engineers why the salesman wasn't totally lying. Was always what we claimed a field engineer's position was. Then that also ran into VxWorks, which I'm not even sure who owns it now. Used to be briefly, not too long ago, owned by Intel. Of course, I've run into some various embedded Linux, some better than others. Hard Hat Linux was a good attempt at it. VxWorks has a long, patchy history of both ownership and different levels of capability of their different offerings. Like I said, it all depends on the application, and a lot of it depends on what you're used to using. Nobody wants to learn the ins and outs of an operating system 2 months before they have to release something. So they usually go with what they know. So, in any case, while we were in this poor little loop here, I said while steps is greater than 0, and steps came in at 15. And the first thing we did was add some number, or subtract some number from the pitch, change the craft's pitch, wait a tenth of a second, and then come back up here and say, is steps still greater than 0? Well, yes, because we didn't do anything about it. So, in order for this to work, we need to make steps equal to steps minus 1. So that every time it goes through all of these lines of code, steps gets a little smaller until steps eventually becomes 0. And this while loop finishes. And we jump down to here to print, or in this case, display pitch. Right? So you see where that was a problem?
Yeah.
Otherwise it would be called an infinite loop, which you never get out of. And if you end up in an infinite loop while you've got the thrusters on, as you've seen in various Kerbal videos before, and your thrusters stay on, well, you end up in the stratosphere. The wrong stratosphere. You end up in the heliosphere instead of the planet sphere. So in any case, this, of course, kind of verbiage looks a little pained. So they made it a little easier. They said, you don't really need to do that. You can actually just say steps minus minus. And that takes steps and makes steps minus 1. Similarly, you can say steps plus plus, which says take steps and add 1 to it. In this case, if you did plus plus, it would go on not quite forever, because it would start with 15, and then it becomes 16, 17, 18, 19, 20, 21, to 4 billion, at which case it would go get to its 4 billion number, and then flip over. back to 0, so it would eventually get to notice. I wish it was editing the game. It's not really editing the game. It's describing how the game code would be in C. So, or if it were in C. So we want this to be steps minus minus, so it only does it the 15 times. And then we do our display. So I think we've got the general gist, right? Ascent, stage, much the similar kind of stuff. There we go. Bring that to the foreground. So the ascent stage would be very similar, right? We activate the staging, which is the launch. We wait until our altitude is above 1,000, etc., etc., right? Pretty straightforward. So let's go ahead and launch this guy. We've been spending a lot of time in here showing all this.
An hour.
So let's go ahead and launch this guy. Now the only difference between this one and the one we launched before is he's launching from Earth instead of Drew. Good luck. It's not going to get very far. There we go.
So you have to take the notepad down.
I did.
Okay.
Get the music on. There we go. Same script, auto running, throttle up.
Oh, boy. It just goes.
And it goes for launch.
Is this a KSP mode on?
No, this is Simple Rockets 2. Which, I'm not sure how, oh.
Oh, that was split second.
That's kind of rather annoying that it doesn't continue when you're not looking at it.
What's up with that?
I don't know, it's just the way this one behaves. So, you'll note we're at only 6,000 meters. We've already started our kickover. We're doing a number, we'll do one more kickover at 1,500. But we're not getting anywhere near orbit. We're we're only 20 kilometers up. And that's because Drew is a much, much smaller planet. There we go, we're going to go for our staging event here shortly. Whee!
It looks pretty cool. Way better graphic.
Right, lots of detail. Well, this is the new real solar system mod for Simple Rockets. Well, Simple Rockets 2. So, no, we're not getting anywhere near the kind of apoapsis we had before.
Right?
We're not even going to get out of the atmosphere, I don't think. Going to burn out at 20% of the core stage fuel and then run to the apoapsis and then attempt to get into orbit, which, not so much. Really should have created an abort action group, I think they call them in this, or what do they call these things? Yeah, activation panel. I have just the solar panels. I should really like make an abort or something, because 73 kilometers. I don't think that's technically space, though, is it? It's 60 miles.
60 miles.
So that's 120 kilometers? I don't remember. I don't have my googly box in front of me. Are you hearing the sound effects?
Yes.
Ah, good. So we're going to cruise to our apoapsis. And we're going to light this core up again and attempt to get to... Oh look, the planet's invisible. There it is. Look how much bigger it is.
Hi.
Oh, here we begin our fruitless orbital insertion burn. As we just desperately try and fly. Oh, core jettison. Ah, we missed it. Yes, we originally programmed this in Vizzy. A couple episodes back, we did the just playing with it, and then our altitude is failing us. See if I can change our attitude here. We need to be looking up. Go up.
That is. It's 20%.
Go up.
20, 31.
This cone
It's
is
not
the
going
direction
up.
he's actually going.
It's not going up.
It was much more successful on Drew, I promise you. Just look at the last one. Ah! But you know, this is as good a time as any. Let's pop them solar panels, shall we? Whee! Oh, now this is just fake. They should be like being blown the hell off. How in the world do my solar panels stay on? I don't know, 52,000 meters? But then enough atmosphere to not smack the solar panels, maybe. I don't know, it should be interesting on ring entry anyway.
Low Earth orbit, very, very low Earth orbit.
I don't think it's quite an orbit either. We have no periapsis. And now we have no fuel. So we're just coasting along. I don't know quite why it's wobbling around so much.
Why is it wobbling around so much?
I don't know.
Nice music.
I suppose we should try and lock ourselves to retrograde, but we can't. Yep, the aerodynamics are messing with us. Ah, it's no good. We're just gonna have to ditch this. Bye-bye! Alright. Now, luckily... Where'd that go? How in the world did it fly away? Luckily, our aerodynamics are such that the capsule will manage to stay retrograde nicely. And of course, who needs a heat shield? You're not all that high up. Or going even all that fast. Now we hope that our parachute still contains the appropriate program. And also, did I code it? Yeah, I coded it for like 5,000 meters. So the parachute has a very small program in it that says start up when everything else starts up, and then wait until you're above 5,000 meters, and then wait until you're below 1,500 meters. And at below 1,500 meters, and by above and below I mean greater than or equal to and less than or equal to, below 1,500 meters, pop the parachute. Actually, it activates the final stage, whatever the final stage is, which is pretty much always the parachute. I was also thinking it might be fun and very entertaining next time to code like an escape tower. They have this escape tower that you can put onto the capsule.
Yeah.
Right? Or I can just stick some sort of linear engines on the side as escape engines. And there's actually an event in the Vizzy called If Part Explodes, or When Part Explodes. On part explosion. Do this batch of code. So we're going to try and code an automatic escape sequence so that when we intentionally blow up the center core, that our capsule oh, there we go. Parachute deployed.
Oh.
Whee! So yeah, that'll be the next thing I want to do is have a code the safety system, right? I'm all about flight safety. We should code the safety system in case your center core randomly explodes. And of course, they've helped us because apparently any part you check, you can choose to randomly explode. And I guess that kind of reflects the reality of space travel. At any given moment, something might go boom. Where's the sun? Not seeing it. So we're just cruising along. Yeah, we're coming down pretty good. 19 meters per second is not too... I would rather it be like 6. Somewhere in the single digits. Blurk. Now watch this fun part. Yeah, circulize burn. Sure, you're doing a circulize burn.
What is that tumbling thing?
I don't know what the tumbling thing is.
Let's see if a bunch of people came in here to watch you.
It's somewhat interesting, though. So,
is it?
So next time we'll go ahead and code up our escape system and try that out. We'll just add that in Vizzy. We won't worry too much about the real-time C from here on out.
So you don't have to pick up the capsule and get anything and all that stuff. That's applicable.
Right now, there's no like. Yeah, there's no money to be had that I can tell. Actually, let's take a look at that.
Well, that was pretty interesting.
That's in flight here. And then, I actually haven't taken too close a look at these other things. But if you just say go, we have a build a craft in a sandbox. You know, maximum thrust build challenge. That can exceed the speed of 750 meters a second before it reaches an altitude of 2 kilometers. Must fly straight up.
Then you'll fail this challenge.
Yeah. So they do have these kinds of things. Build challenges. A low flight. Hey! I should bring it to the floor.
You should have done that.
Without going above 5,000 meters. Well, I did manage more than 5,000 meters at least.
We haven't done an orbit yet, so... Well, that's a goal.
Not from planet Earth. This was our first planet Earth launch, so... Drew makes everything easier. Fly this rocket as far as you can. Atmospheric drag can really slow you down. So, I remember the optimum trajectory challenge. It was basically launch and go at 45 degrees. Is pretty much your... by and large. Yeah, I don't believe this is at all a clone of KSP, that's for sure. This is really more about the simulation, automation, simulated automation. And then, you know, these challenges, which at least give you something to target, right? And give you some degree. Let's try this. Is it the optimum trajectory? Given a super small rocket, you say. Let's see what kind of small rocket we get. Now this is where coding your... Oh. Well, I would say that's a super small rocket. It's itty bitty. Itty bitty bitty.
Looks like a pretty fun game. Definitely not just a wannabe clone of KSP. No, it's definitely not.
No, it's far more. I don't want to say realistic graphics because Kerbal is Kerbal. It's a different solar system. And even this started with a different solar system. But at least it does have a real one. So eventually we want to see what we can build for our own plans in the future. So let's throttle up. Let's lock the current nav heading, which is straight up. Launch and immediately go to 45 degrees. If the goal is to get as far away as possible, and this is a ballistic rocket, then generally speaking, although I didn't actually hit 45 degrees, so we may... This is definitely one of those challenges where I don't know if they'll let you code it, but if you coded the launch, well then you could perfect it, right? Now here's the thing.
What is that thing supposed to do?
Well, it's the Lawn Dart Challenge.
Lawn Dart Challenge.
It's not actually called that. It's called the the Optimum Trajectory Challenge, which is to say, how there we go. I'm actually trying to sail this thing, believe it or not, by putting it sideways into its air path. I'm hoping to kind of get it to skip off the air and go further. Ow! You have failed.
Oh.
Distance traveled greater than 15,000. Oh my god. Well, then we're going to try this differently. Just this one more flight. Because otherwise, you get like in this retry loop. Where you do this for 6 hours.
Yeah, no.
No, we'll try it just the one more time.
Alright.
I'll do it with the opposite kind of goal, which is instead of 45 degrees, we're going to go for, shallower. We're going to aim for like 30. But first, we do have to lock it on there. And we're just going to keep it at 30 and see if we can get it to bounce off the air and all like that on the way down. So, throttle. And launch. What we want to do is stay as streamlined as possible until we reach the top of our arc. So that we apply as much of a ballistic arc as possible. I suppose we could do that by just locking prograde at this point. Let's see, greater than 15, huh? Here we go. Doesn't look like we're gonna make it. But that just goes to prove you don't necessarily know what you're talking about the first time you try it. Or even the second. Here goes the Kablowie. Let's zoom away from it, shall we? Let's get to see it in all its glory. rocket lawn dart. God, that's a harsh explosion sound. Hey, I still have an engine. Look at my beautiful engine flapping in the wind. Don't you love that you got some parts left over?
Big bummer.
Failed again.
Ouchie. That's right. It looks like it wants to stand up like it's got a weeble on the bottom.
I know, right? Notice how quickly we already started to get back here and we're already ready to go again, and you can't really stop it. You gotta go, oh, we're flying!
Okay. 121, I'm out. You can lawn dart all you want. There are people in here watching you lawn dart, though.
See how quickly you can restart, though? I like that about it. We call it, in software, we call it the burn and churn cycle.
Right?
Where you write stuff, and then back in the day you had to burn it to an EEPROM, and then you would run it, and you'd see if it worked. And you'd churn, and do that again, and do it some more. Hopefully make some changes along the way that make sense. Well, this thing's just barely breaking 11 kilometers. I don't know what the deal is. But I'm thinking it might be pizza time.
Yeah.
Pizza time!
Pizza
Gotta
time.
go. One
Thank
more
you all
kaplawi.
very much for hanging out with us tonight. I really appreciate it. I had fun.
Thanks. We'll see y'all all next time.
Take it, button. Yay! We just did it.